this is a little bit of an extension of the last video we did with linear transformations. It turns out that linear transformations are well described by matrices. However, the matrices are dependent on the basis we are using. So in this video, we are going to emphasize the basis corresponding to the basis we may be using corresponding to the, I'm sorry, the matrices that we use for each linear transformation are dependent upon the basis we are using. There we go. So I'm going to try to make that a little more clear as we go along this video. So first, let's talk about basis, the basis we use. This point here can be thought of as 2, 1, 3 because we go 2 units in the x direction, 1 unit in the y direction, and then 3 units in the z direction. So we go towards us from the origin, to the right as we see this, and then up again as we see that. And everybody thinks of this as pretty normal, standard, unique. But in reality, that assumes that we are using this vector, which is this direction, as first coordinate, or as actually this coordinate tells us that we're using this vector first. And then we're using this vector second, and then this vector third. So there's a lot of assumptions going on when we describe a point with those coordinates. We're assuming, again, we're using this, that, not only those, but in that order. If we were to write 3, 1, 2, we would say, well, that's not true. But actually, it depends. If we use, I need to draw a new set of little vectors. If we were to use this as first, second, and first, then those coordinates would indicate the same point because we would go up 3 units, 2 units across, and then 1 unit to the right, and that would lead us to this point. What I'm trying to say is the way we write the coordinates of a point are 100% dependent on the basis we're using, and that is the basis. Not only the basis, the vectors that we use as the basis, but in addition to that, the coordinates are dependent on the order in which we use the basis. So again, if this is first, second, and third, then this point should be written as 2, 1, 3. But if we set this to be first, second, and third, then this point should be 3, 1, 2. So there's a basis that we are using. Yeah. However, the basis is not set on stone. Yeah. So basis could change depending on application. Yeah. So this is not the best analogy, but think of languages. We have different languages. We use English, but that doesn't mean that is the only language. There is tons of languages: Chinese, Japanese, German, French, Spanish, Italian. I mean, you name it. The list goes on and on. Even within languages, there are dialects, and then there's sign language. I mean, you name it. There's tons of things that now. So why and it isn't that one language is best. If we cannot communicate with sound, then sign language is better, and then there's written language, and I don't know. It goes on and on. Even in computer sciences, there are different languages. And I don't know too much about computer sciences anymore uh, because things have changed since I studied a little bit of computer sciences. But I know there is different kinds of languages. There is C, and there used to be Fortran. I don't even know if the people use Fortran or COBOL, or there's all different kinds of languages. Um, and by that I mean computer languages, and one may be better for certain applications, another one may be better for other applications. So for instance, if you're building a processor, you're probably going to use one language. I don't even know which one. But if you're putting together a website, you're not going to use low-level language. You're going to be using a different language. um, I don't know if HTML is a language. Again, I'm just telling you how much I do not know about computer sciences. But what I do know is that we have different languages depending on the kind of application we are working on. Well, likewise, there are different bases for coordinates of points or vectors depending on the application. And actually, this is easier than languages in general. Um, so when we write down 2, 1, 3, okay, we are assuming we have 2 of these vectors plus 1 of this vector plus 3 of this vector, 0, 0, 1. Okay. Yeah. Notice that those vectors form the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah, so those vectors are in the identity matrix. So from that point of view, we can think of this as the coordinates of a point using the columns of the identity matrix. But that is not the only matrix we can use. We can use, or the only coordinates we could use, what I meant by that, the only base element. So those 3 form a basis for R cubed. So 1, 0, 0, comma, 0, 1, 0, comma, 0, 0, 1 is, now I'm using the singular because this is one set, is a basis for R cubed, which means we can write any point, we can describe any point in R cubed using this. It's kind of like using English. To pretend this is the language of English. So, but except that this is even simpler than English. English is much, much, much more complicated than just 3 vectors. But so this is stating one standard, but that doesn't mean that the standard is unique. We could use French or German or Chinese or Japanese, etc. So, as before we get too far into all different kinds of directions, let's make sure we know what our goal in this video will be. And so first, we want to talk about, well, I don't know if this is the first thing we're going to talk about, but we want to talk about the matrix of a linear transformation. I don't know if this is going to fit in the rest of this page, so I'm going to start a new page. So again, I'm going to put bullets here. One of the things we are going to focus on, our goals, is about the matrix of a linear transformation. Okay, using, and I'm going to label this as I as the basis. So I means the standard basis. If we are in R3, 1, 0, 0, 0, 1, 0, 0, 0, 1. If we were in R4, it would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then 0, 0, 0, 1. If we were in R2, well, just 1, 0, and 0, 1. So that is what I would call the identity basis. And this overlaps with what we already did in the previous video. All right. Then we want to also focus on how to move from one basis to another basis. And the way we will achieve that is by using a matrix. So the question is, um, the matrix, or what we're going to focus on is the matrix corresponding to going from one basis to another basis. Okay, so that's a second goal, one goal, second goal, from one basis to another basis. Now, it turns out that going from one basis to another basis is indeed a linear transformation. Isn't that funny? So going from one basis to another basis is itself a linear transformation. And then finally, we want to combine those two ideas in one matrix. So the matrix corresponding to a linear transformation using different, perhaps different bases in the inputs and in the outputs. So the matrix corresponding to a linear transformation in different bases for the input and the output. And then there is one more thing that we can add to this, which is a narrow view of this, which would be the matrix corresponding to a linear transformation, matrix corresponding to a linear transformation, using or in a non-standard basis. Okay. Okay, so there are four things going on here. This is actually a narrow view of that. This is a combination of those two, and then we can start talking about those two first, combine those two ideas to get to this, and then narrowing down this idea, because this is a general idea, into a smaller idea here. Okay. So now I did speak about languages, and let me stay with the idea of computer languages, because that is less controversial than human languages. So ultimately, though, even though there are different languages, computer languages, ultimately they have to interact with the actual processor. Although, man, that gets complicated, because processors nowadays are very, very complicated. But ultimately, they have to deal with zeros and ones, you know, to the currents that go through the processors, to the chips, the electronic components of a computer. So eventually, everything has to break down to a very, very simple a way of communicating with the chip itself. So even though we are talking about different languages, eventually, you know, oftentimes we have to base ourselves on this coordinate system in some kind of, we got to start with some kind of language. That's what I'm trying to say. Yeah. So at the bottom, at the end, there is some kind of language we have to start with. We cannot just start with nothing. Although some people will say, well, how about, you know, before people started talking, we didn't have a language. Yeah, but maybe we made faces, and that was our way of communicating, you know, an angry face or a happy face or a sad face. Maybe that was already communication. And I don't know, at some point there's going to be some kind of communication that happens. But let's talk about the first bullet, which is transformations. So again, I just want to go back and review this because it is important to know where we're going. Transformations, matrices for transformations, matrices for changing bases. We're going to combine those two to come up with matrices that change bases, and then and that's it, with different bases. And then we're going to use the same base on both ends, in the input and the output, the same base, but not the standard base. So first, let's talk about the standard base, which I'm going to call I, um, and the transformation with that I, and transformations. Okay, so let's start with an example. Example 1. Let's say we have a transformation T going from R cubed into R cubed. And I tell you what, such that T of 1, 0, 0 is equal to, and I'm just going to make this up, 1, actually, I already said 2, so 2, 1, 3, T of, I'm going to keep things simple, 0, 1, 0 is equal to 0, 1, 0, and T of 0, 0, 1 will be 0, 0, 1. So that is a small change from a regular, from the identity. Let me go back for a moment and gee, I'm sorry to interrupt myself, but let me go back for a moment and talk about example 0. T, because this is even a simpler, this is going to be a simple example, but then I just thought of an even simpler example. So if you have any matrix, any vector rather, A, B, C, and the transformation such that it gives you back A, B, C. Okay, so transformation of A, B, C gives you back the same A, B, C. That's the identity transformation. It doesn't change anything. The input is this, the output is the same. That's an A, looks kind of a funny A. Anyway, what is the matrix corresponding to this? Now, this is a transformation. This is like an f of x kind of thing. F of x equals that. All right, so that's the way we read this. Now, it turns out that there is a matrix corresponding to this, and the matrix, a 3 by 3 matrix, so that when we multiply with A, B, C, we end up with exactly A, B, C. And it is a unique matrix. It is going to be the identity matrix. 0, 1, 0, 0, 0, 1. There we go. So when we multiply this matrix, we get A, 0, B, and then C. So this is the matrix corresponding to this linear transformation. And this linear transformation just doesn't change anything, leaves things alone. This is a super, super basic linear transformation. This is the identity linear transformation. Identity linear transformation. Okay, so I wanted to put this in the record before we did another example, which is going to be this one, which is a simple example. So this does not change, does not leave things the same way. It leaves those two, this transformation leaves those two vectors the same way, but this vector changes, is not the same. So the question is, what is the matrix corresponding to this linear transformation? Um, okay, and there's a couple different ways to address that. Um, hmm. um, let's think of finding the matrix in a general way. So I want to find a matrix. Okay, so we want um, matrix A such that um, AX, the column vector X, equals T of X. Okay, so that's our goal. Let's start with a generic X. Okay, so if you apply T to ABC, to the column vector ABC, well, that is the same thing as applying T to A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. Okay, so we're applying T to this. But T is linear. That means that it preserves additions and multiplications by scalars. So this is the same thing as A T of 1, 0, 0 plus B, whoops, times T T of a 0, 1, 0 plus C times T of 0, 0, 1. Okay. Now, T of 1, 0, 0 is, they gave us that in the part of the problem. It is 2, 1, 3. So we have A times 2, 1, 3 plus B. Now, 0, 1, 0 stays as is. 0, 1, 0. And so does 0, 0, 1 plus C 0, 0, 1. And that turns out to be 2A, no B, no C. And 1A plus 1B, and no C. And 3A plus no B plus 1C. Plus C. There we go. Okay. So we want to find a matrix A, a 3 by 3 matrix. So when we multiply with A, B, C, we end up with 2A, A plus B, 3A plus C. Once we have this, then it's easier to figure out what this matrix will be. Okay, so 2A, when we multiply the first row, we do not know initially what this row should be. But we want to have two of those, no B and no C, because we end up with just 2A. So no B, no C, 2A's. Here we want to end up, when we multiply this row with this column, we want to end up with 1A and 1B and no C. So 1A, 1B, no C. And when we multiply this row with this column, we want to end up with 3A's, no B, and 1C. 3A's, no B, 1C. So the matrix we are looking for is 2, 1, 3, 0, 1, 0, 0, 0, 1. That's the matrix corresponding to the linear transformation. Now, what is the benefit of having the matrix? Okay, so let's follow up. We're not, technically we finished with the goal, but there is more to this. So the question I want to follow up with is, what is the benefit of having this matrix? Question mark. All right. First, I'm going to tell you. I'm going to follow up with a problem, and then we're going to answer this. So let's say within this problem, I want to know how much t of, I'm just going to make this up, 6, 7, 8 is. Okay. So again, we want to know. So again, I'm going to start answering this question with this other problem. Okay. Say we want to evaluate or find this guy. Well, with the information we have, this information, we have to break this up as 6, and I'm actually taking a shortcut. 6 of those which transform into 213, plus 7 of those which transform into themselves, 0, 1, 0, plus 8 of those which transform into themselves, 8, 0, 0, 1. So that is equal to 12. 6 and 1 is 6. 6, 18. I meant 6 times 1. Plus 070 plus 008. So we end up with 12, 6 plus 9, 15, 18 plus 8, 26. So there we have it. T of 6, 7, 8 is 12, 15, 26. And the way to figure this out without using the matrix is by breaking this up into its individual base elements, transform the elements by themselves, by the transformation, by the given transformation. And then we figure this out. Or we can simply multiply the matrix 2, 0, 0, 1, 1, 0, 3, 0, 1 with the original vector 6, 7, 8 and obtain the answer at once. I was trying to snap my fingers. They weren't snapping too well. Anyway, 12, 6 and 7, 15, 18 and 8, 26. See? So what is the benefit of having a matrix corresponding to a linear transformation? If you want to map any vector using that transformation under that transformation, it is a matter of multiplying by the matrix, and voila, we are done. We're finished. That's it. No more to do. Okay. Generally speaking, if you are given the base elements, the transformation of the base elements, the transformed base elements, the image, that's a better way to say, the image of the base elements, then the matrix is very, very easy, because the matrix will be invariably those vectors themselves. See, 2, 1, 3, 2, 1, 3, 0, 1, 0, 0, 1, 0, 0, 0, 1. So let's do a second example. Okay, so second example. Let's say t goes from r cubed into r cubed, and the information we have is that t of 1, 0, 0 is, and I'm going to make this up, 2, negative 1, 0, comma, t of 0, 1, 0, again, 5, 6, 7, and t, comma, I'm going to put it here, I guess. I can try to, no, I'm going to put it down here. T of 0, 0, 1 is 0, 3, 4. Okay, so the question is, what is the matrix corresponding to this linear transformation? And the answer is very easy. So we're going to typically label A as the matrix, and it is just going to be 2, -1, 0, 5, 6, 7. Oops, I didn't mean that. I meant 2, -1, 0, 5, 6, 7, 0, 3, 4. There we go. So if you want to map um, absolutely any vector, say 11, 12, 13, if you want to find this, all you have to do is multiply this matrix 2, 5, 0, -1, 6, 3, 0, 7, 4 by 11, 12, 13, and then we're going to end up with the answer, whatever that is. With, yeah, yeah. So that this problem, if we're given those, which are our standard basis, then we're good. So if we are given the outputs or the image outputs of standard basis elements, then finding matrix A is easy. Because all you have to do is write them in the correct order. If this is, if I gave this one first and this one second, this one third, check that. See, and we are assuming we have an order. This is the order: first, second, third. X, Y, Z, and this is X, this is Y, this is Z. So there's a lot of assumptions going on here. Yeah, so the order has to be correct. If you put them in a different order, then your basis is different. So the basis is not only the vectors. When we are talking about coordinates, these are really the coordinates, because we are assuming that the X is first, the horizontal is first, and the Y is second. So coordinates take into account the order in which the base elements are written. And we are talking about coordinates. Okay. So, yeah. Just check order is correct. Yeah, make sure that the order is correct. Okay, let's complicate this problem a little bit. What if 2, 3, sorry, 3. So complication. We have a linear transformation T from R cubed into R cubed, but now there is a difference. I'm not going to give you T of 1, 0, 0. I'm going to give you T of 1, 2, 3. And let's say it is 5, 6, 7. And I'm not going to give you T of 0, 1, 0. What about 3, 1, 1? And that is going to be 0, 1, 2. And what about T of, I don't want to make it too complicated. 3, 2, 1. That should be okay. And that being equal to, again, some random number. Let's put a negative 2, 0, and a positive 2. Okay. Whoa. So what is the matrix? I don't know. I don't know the answer. That gets really, really complicated. Now we're still using the standard basis, X, Y, Z as normal. So what is the matrix corresponding to this? This is, wow. So remember, example 2, if we're given the base elements, finding the matrix is easy. It is just a matter of rewriting the outputs in that order, and that's it. We're done. If we're looking for the matrix, this is the matrix. We're finished. There's nothing else to do. Here, the difference is that we are not given this in standard units. Interesting. Interesting. Yeah, this is very, very interesting because we could almost jump, using this example, we could almost jump into here at once. Okay. I almost want to do that. Yeah, let's do that. So not the matrix, not the matrix. Exactly. Is if you put down 5, 6, 7, 0, 1, 2, negative 2, 0, 2, if you just put the outputs, there is something to be said about this. This would be true if the inputs used coordinates using basis 5, 6, 7, rather 1, 2, 3, 3, 1, 1, comma, and 3, 2, 1 in that order. And the outputs, I believe, would not be correct either. So we're going to come back to this example using different bases, but this is just a side note for now. Side note. We still going to want to solve this problem. So whoops, the side note starts here. Yeah, this is not the answer, by the way. This would be the answer if we allow different bases. So that is not the answer. But the question remains, what is the matrix? We don't have the standard identity vectors, then what is the basis? All right, so here's one way to go about that. So our goal is to find what is T of 1, 0, 0, question mark, because that would actually be the first column of the matrix. Man, so what is T of 1, 0, 0, question mark? We don't know. So first, we want to rewrite 1, 0, 0 as a linear combination of 5, 6, 7, so A times 5, 6, 7, plus B, oh, I did not mean that. I mean 1, 2, 3. Let's just write it up down here, 1, 0, 0. We want to write it as a linear combination of 1, 2, 3, and 3, 1, 1, and 3, 2, 1. So 1, 0, 0, we want to write it in this as a linear combination of those 3 input vectors. I want to make sure I have the correct input vectors, 1, 2, 3, 3, 1, 1, 3, 2, 1. Okay, so let's do that. That means that A plus 3B plus 3C, A plus 3B plus 3C equals 1. And 2a plus b plus 2c equals 0, and 3a plus b plus c equals 0 as well. Okay, so we want to solve this um, system of equations. Next. And solving this system of equations yields a equals negative 1 over 8, b equals 1/2, and c equals negative 1 over 8 again. I just took the time to figure this out, but let's double check. So 3b's, so that's 1.5. That gives us 1. That seems to work, because then we subtract 4/8, which is a half. Negative 1/4 plus a half is a quarter. Yeah, minus a quarter, that works. So the second equation works. Negative 3/8 plus a half, that's 1/8, minus 1/8 equals 0. So this combination works. Okay, so 1, 0, 0 is 1, 0, 0 is negative 1/8 of 1, 2, 3 plus 1/2 of 3, 1, 1 minus 1/8 of 3, 2, 1. Yep. So t of 1, 0, 0 will be negative 1/8 of, okay, so now that we wrote 1, 0, 0 as a linear combination of 1, 2, 3, 3, 1, 1, and 3, 2, 1, we can write the output of 1, 0, 0. It is going to be negative 1/8 of the output of 1, 2, 3, which is 5, 6, 7, plus 1/2 of not 3, 1, 1, but the output of 3, 1, 1, which is 0, 1, 2, minus 1/8 of the output of 3, 2, 1, 3, 2, 1, which is negative 2, 0, 2, negative 2, 0, 2. Okay, and that's going to be, I'm going to try to do it all at once, negative 5/8 plus 0, so I'm not going to write that down, and then double negative, so plus 2/8. That is for the first component. So yeah. For the second component, we got negative 6/8, multiplying those two, plus a half. I'm going to write that down as 4/8 and nothing. Good. And then for the third component, I'm going to try to squeeze it in here. We got negative 7/8. Plus 1, which is 8/8, and then minus 2/8. So that is negative 3/8, negative 2/8, and negative 1/8. This, of course, simplifies down to negative 1/4. Okay, that is the output of 1, 0, 0. So that is on the first column of the matrix we are after. Now we have to do this process over again for 0, 1, 0 and 0, 0, 1. Okay, so I'm going to save this column vector. I'm going to start all over. So 0, 1, 0 should be a linear combination of 1, 2, 3 plus 3, 1, 1 plus 3, 2, 1. Oops, C. That's going to lead to a system of equations, the same thing we did before. A plus 3B plus 3C equals 0 this time. 2A plus B plus 2C equaling 1. And 3A plus B plus C equaling 0. So 3A plus 1B plus 1C equaling 0. And we want to solve this system of equations. And we get A equal to 0, B equal to -1, and C equal to 1. Those two add up to 0. If A is 0, if and B is -1 and 1, I'm kind of double checking. 0, so -1 plus 2 is 1. 0, and sure, -1 plus 1 is 0. So that works, and that means that, okay, 0, 1, 0 is exactly no 1, 2, 3 vector minus 3, 1, 1 plus 3, 2, 1. Yeah, 3 minus 3 is 0, 2 minus 1, 1, 1 minus 1, 0. So we're good. And that means that T of 0, 1, 0 is going to be 0 of the transformation of 1 to 3. The transformation of 1 to 3 is 5, 6, 7, minus the transformation of 3, 1, 1, which is 0, 1, 2, plus the transformation of 3, 1, 2, 3, 2, 1, which is -2, 0, 2. Okay. So, let's just do this. So that is 0, -1, -2. I'm just multiplying by -1 or moving this into the vector. And then plus -2, so that is -2 plus 0 plus 2. So we end up with -2, -1, 0. Okay, we got 2 down, 1 to go. Now we're gonna do the same thing for 0, 0, 1. We did this for 1, 0, 0, and we got this weird vector with fractions. 0, 1, 0 gave us a nice vector without fractions, some negative numbers. And now let's see what happens with 0, 0, 1. So let me do that on a new page. So next we want to change 0, 0, 1 into a linear transformation of 1, 2, 3, and 3, 1, 1, and 3, 2, 1. So as in the other examples, we want A plus 3B plus 3C equal to 0, 2a plus b plus 2c equal to 0 again, and 3a plus b plus c equal to 1. This one. Yep. In this case, we obtain a to be 3 over 8, b 1/2, and c negative 5 over 8. I'm trying to think. So we got 3 of those, and 12, that's 15 minus 15. Yep, this is the same thing as 4 over 8. So it looks like that works there. Let's double check here. 6/8 plus 4 is 12. Okay, so 6/8 plus 4. Oh, that's 10. 10/8 minus 10/8. Yep, that works. And then 3, so that's 9/8. 9/8. No, 6 rather. No, 9. 9/8 plus 4/8. That's 13/8 minus 5/8. Oh, that's 8/8. So that works. So this combination works. This is the coefficients of those. So t of 0, 0, 1 will be 3/8 of t of 1 to 3, which is 5, 6, 7, plus half of 3, 1, 1. I'm almost memorizing those by now. Not quite, but minus 5/8 of negative 2, 0, 2. So now we just gotta multiply this out, and that is gonna be 3 times 5 is 15 over 8. 3 times 6 is 18 over 8. 3 times 7 is 21 over 8. Plus, this is the same thing as 4 over 8. So I'm going to work, and since I'm going to combine with eighths, might just as well think of this as 4 over 8. 4 times 3 is 12 over 8. 4 over 8 and 4 over 8. Plus, because I see a double negative, 10 over 8, 0, and minus 10 over 8. So 15, 27, 37, 18, 22, which we're going to simplify as 11 over 4, and 21, 25, 15. Okay, so now we are ready to provide the answer. A, the matrix corresponding to this really, really complicated transformation. So again, this is example 3. We have a complication because we are not giving the standard basis. We're giving some other basis. This is a basis, but it's a weird basis. It's just totally random numbers. But they will come build the whole of our cube. It's just in a weird, different way. It's kind of like using a different language. If we use French, you will be able to communicate is just going to be different. It's going to sound foreign if we are not thinking French, but we can still communicate. Anyway, so according to that basis, this, and even that is not even totally correct. Anyway, the 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 matrix will be -3/8, -1/4, -1/8. That's the first column. The second column, oh, that one was nice. -2, -1, 0. The third column, 37/8, 22/8, and 15/8. So that is the matrix. Corresponding to this linear transformation. We can factor out the 8 and have -3. Since we factor out the 8, the 1/8 we have to multiply, so -16, 37, -1, -8, 22, -1, 0, +15. So there is our matrix corresponding to the linear transformation. So A is equal to that. Now, how can you be certain? Okay, if we plug in 1, 2, 3, we better get back 5, 6, 7. That's one way to, and actually, if we want to be positively certain, what we want to do is plug in 1, 2, 3, get this answer, 3, 1, 1, get this answer, 3, 2, 1, and get this answer. All three have to work. And then we are completely positive we are correct. Let me plug in 1, 2, 3. So to check, I think I'm only going to check one vector, but if we wanted to check everything, then we have to multiply all three vectors. So -3, -16, 37, -1, -8, 22, -1, 0, 15. We want to multiply this with 1, 2, 3, which is the original information they gave us. So -3 minus 32 is -35, plus 3 times 37. Whoa, where's my little calculator? Here it is. 37 times 3, 111, minus 16 times 2, so that's minus 32, minus 3 times 1, equals 76. That makes me nervous because 76 divided by 8 is 9.5, but we are supposed to get 5. Let me check this. Okay, after looking at this for a moment, I realized there are two mistakes. One that is, well, here's the first one. -1/4, when we factor out 1/8, we should multiply that by 2. So that should be a -2. And that should carry down here. But that did not change what I was getting wrong here by this computation, the first computation. So I have to go back to this. And I realized there's a mistake here. When transforming 0, 0, 1, we have to transform 1 to 3, which is this. And we have to transform 3, 1, 1, which is not that. And we have to transform 3 to 1, which is that. So this is the one we have to change. And the transformation of 3, 1, 1 is 0, 1, 2. So this should be 0, 1, 2. Okay. So that is 0, 0. This one is okay because that was 1, and that should be 2. So that should be 8 eighths. Okay. 15 and 10 is 25, not 37. All right. 18, 22, that's all right. 21 and 8 is 29, minus 10, 19. So that should be 19. This guy. And that means that our matrix has to change accordingly. 25 over 8. This one should be the same, and that should be 19 over 8. So that should turn into 25 and 19. 25, 19. And this one should also change accordingly. So that's why we want to double check our work. 25, 19. So let's redo this. Negative 3, negative 35, plus 50, no, plus 75 is 40, divided by 8 is 5. Good. So the first output is correct. We're supposed to get 5. The next output should be 6. Let's see if it is true. Negative 2 minus 16, negative 18 plus 66. 66 minus 18 is 48. Divide by 8, 6. That checks. And then negative 1 plus 57, that is 56. And 56, I know, divided by 8 is 7. Oh, but then we don't need the 1/8 anymore because I'm already dividing by 8. So yes, that checks. And then we should check the other two vectors. So thanks to that checking, I was able to find the mistakes. So there was one mistake here that was not found by this because I was checking and I found that independently, but I definitely found that this has to be different. Wow, 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 wow. So that is the matrix. This is the answer that we are after. Okay, so that is as complicated as it will get just for the first complication. But that is the biggest complication we may have. What I meant to say in the first bullet. So far we've done only this bullet. Now we need to do the second bullet, which is how to change or finding the matrix corresponding to a change in coordinates. So now we want to change coordinates. So we want to find the matrix to change coordinates. Let's start with an example, a problem. Okay. Our standard matrix, rather, our standard coordinates use the basis 1, 0, 0, 0, 1, 0, 0, 0, 1 in that order. Let's call that I for now. Okay, say we want to change to a new basis. And I'm going to piggyback a little bit on the previous example. 1, 2, 3, 3, 1, 1, and 3, 2, 1. I'm going to label this basis as W, big W, because of weird. It's a weird basis. And it's an arbitrary basis, and it's kind of weird, I have to admit. So I want to change coordinates of that into that. Now, whenever you write down A, B, C as a vector, that means A of those plus B of those plus C of those. So when we write down, again, A, B, C, we are assuming we are using this basis in that order. So that is equal to A 1 O's plus B of these guys plus C of 0, 0, 1. But we want to write it as X of 1, 2, 3 plus Y of 3, 1, 1s plus Z of 3, 2, 1s, which is going to give us the coordinates X, Y, Z using the basis W. See, when you say anything, when you say a coordinate, a set of coordinates, we take into account a basis. And that basis changes depending on the, rather, the coordinates change depending on the basis. Yeah, the coordinates, occasionally the basis will be the same. Rather, the coordinates will be the same. That would be a good coincidence. But generally speaking, the coordinates will change if the bases are different. So we want to know what the coordinates are for this same point ABC using the basis, this weird basis, which means we have to solve this equation for X, Y, and Z. Okay. Yeah. So 1x plus 3y's plus 3z's, 1x, yep, 1x, so just 1x plus 3y's plus 3z's equals just A. 2x's plus a y plus 2z's equals B. And 3x's plus y plus z equals C. So we want to solve this system of equations for X, Y, and Z. I'm trying to figure out what the how to do this most efficiently. Yeah, I'm gonna draw the matrix corresponding to the coefficients 1, 3, 3, 2, 1, 2, 3, 1, 1, and perhaps we can find the determinant. So I think I'm going to use Kramer's rule to figure this out. Solve for x, y, z using Kramer's rule. We could also use just the row. We can row reduce the system of equations, well, the augmented system of equations, but I think it may not be a bad idea to use determinants. So let's see, that is 1 times 1 minus 2, negative 1, minus 3 times 2 minus 6, negative 4, 2 minus 6, negative 4, plus 3, 2, minus 3, negative 1. Let me double check. So 1 minus 2 is negative 1. 2 minus 6 is negative 4. 2 minus 3 is negative 1. And that is going to be negative 1 plus 12 minus 3 equals 8. And I had a suspicion that it was going to be 8 because the system of equations is very similar to the system of equations we had earlier. Remember, we were solving for 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we ended up with a bunch of eighths. So that is the reason. Okay. But now because we're using Kramer's rule, we're going to substitute the first column with A, B, and C. So this is the determinant of the matrix, the determinant rather of the system. Determinant on X will be A, B, C, 3, 3, 1, 2, 1, 1. I'm going to use this column to expand the determinant. So we have A times 1 minus 2 is negative 1, minus B times 0, how convenient, plus C times 6 minus 3, 3. So we end up with negative A plus 3C. Okay, let's save that. Delta Y will be 1 to 3, A, B, C, 3 to 1. I'm going to expand it with this column. So we have negative A, starting with that, times 2 minus 6, 2 minus 6, negative 4, plus B, 1 minus 9, negative 8, minus C, 2 minus 6, negative 4. So we end up with 4A minus 8B plus 4C. Yeah. Let me double check a few things real quick. So negative A, 2 minus 6, negative 4, B, 1 minus 9. Ooh, negative 8. Yeah, I did put the negative 8. And then C, 2 minus 6, negative 4. It looks right. We're going to double check, of course. Delta Z equals 1, 2, 3, 3, 1, 1, A, B, C. And now we're going to expand with respect to this column. So we have A, 2 minus 3, negative 1, minus B, 2 minus 3 is negative 1, B, 1 minus 9, negative 8, plus C, 1 minus 6, negative 5. So that is negative A plus 8B minus 5C. So in order to solve this system of equations for ABC, and remember, X, Y, and Z are the coordinates of ABC in a standard basis. X, Y, and Z are the coordinates on this weird basis. Yeah, that basis is totally weird. I mean, 1, 2, 3, 3, 1, 1, 3, 2, 1. Where do they come from? I just from the thin air, I just made them up. So that yeah, they're a weird basis. So ABC, the coordinates ABC, which are on a standard basis, will be where is it? Oh, okay. We're going to divide by 8. Let me write down what we have so that we know what's going on. So X is equal to negative A plus 3C over 8, comma, Y is equal to 4A minus 8B plus 4C over 8. And Z is equal to, parenthesis, negative A plus 8B minus 5C over 8. The reason why I use parentheses is because I'm using a slant fraction line. And so this, if I don't put the parentheses, only this is divided by 8, but not everything. So everything is divided by 8. We can factor out the 1 over 8. And so the new coordinates are going to be negative A plus 3C, negative A plus 3C, 4A, 4A minus 8B plus 4C, and then negative A plus 8B minus 5C. Which, by the way, can be rewritten as 1 over 8, a 3 by 3 matrix times A, B, C. Oh, and these are the coordinates in the weird, those are coordinates in the weird basis. So that is negative 1, 0, 3. 4, negative 8, 4, negative 1, 8, 5. Yep. And that will give us the coordinates in the weird basis. So that is equal to X, Y, Z, which are the coordinates on the weird basis. So the question is, how do we change from standard coordinates to weird coordinates multiplied by this matrix, including the 1 over 8? Now let's make sure we are correct. So the answer, let me write down a conclusion before we check that we are correct. So the matrix to change I coordinates into W coordinate is 1 over 8, negative 1, 0, 3, 4, negative 8, 4, negative 1, 8, 5. How can we be sure? So that is the conclusion. Um, One way to go about it to check is to multiply one regular way is to change 5, 6, 7, rather 1, 2, 3. Yeah. If we change 1, 2, 3 into weird bases, then we're going to end up with 1, 0, 0. Because remember, the coordinates tells us how many of the base elements we have. So one of those, so 1, 2, 3 is one of those, none of those, none of those. Let's make sure that that is the case. So multiply negative 1, 0, 3, 4, negative 8, 4, negative 1, 8, 5 by 1, 2, 3. And let's see what we end up with. So negative 1 plus 9, 8. 4 minus 16, negative 12. Plus 12 is 0. Okay. Negative 1 plus 16, 15. Whoa. Should I have a negative 5 somewhere? Negative 1 plus 16 is 15, but then plus 15 is 30. Did I miss a negative 5? Oh, there's a negative 5 there. Yeah. And the negative 5 is there. So there should be a negative 5 here. And that means there should be a negative 5 there. See, it's good to double check because then I can detect mistakes. Even though that was a little bit of a typo, and I'm not making excuses, that's a mistake nonetheless. It's good to double check. So again, negative 1 plus 16 is positive 15 minus 15, 0. This is coordinates in the weird basis, and that is equal to 1, 0, 0 coordinates on the weird basis. That means that if 1, 2, 3, which is in the normal basis, 1, 2, 3 goes into 1, 0, 0 in weird basis. It's kind of like changing English into French. We're changing, yeah, so that, which one is right? That's not fair. That's not a fair question. What do you mean which one is right? For the French, this is right. For the people who speak English, this is right. So that's not, that we cannot compare. Um, um, yeah, it depends on the language we're using. So the language is the base. If we are using the base 1, 2, 3, 3, 1, 1, 3, 2, 1, 1, 0, 0 means 1, 2, 3 for our regular basis. Yeah, yeah, that is interesting. That is very interesting. And if we plug in 3, 1, 1, yep, 3, 1, 1 and 3, 2, 1, we should end up with 0, 1, 0 and 0, 0, 1 respectively. I think a better analogy, now as I'm thinking this, I'm talking it out, probably a better analogy is binary numbers. So 1 in decimal is 1 in binary. Let's put a little 2 indicating that it's binary. 2 in binary is not 2, it is 1, 0 in binary, because that's what it is. 3 is 1, 1 in binary. 4 is 1, 0, 0 in binary. So which one is better? Well, it depends. If we're doing binary, then this. If we're using what we have used, we ourselves since we were children, well, then this is better. But that doesn't mean that has no value. This is the way we use in machine language. And all the technology we use is, well, not all the technology, but all the computer technology uses the binary numbers. So yeah, so which one is better? It depends. I think this is a way better analogy than languages now that I think about it. Um, so the same thing works out here. Which one is better? Well, it depends. If our basic vector, so if we have an application in which 1, 2, 3 is a very natural vector to use, then we perhaps want to change all our vectors into this coordinate system. So 1, 2, 3 would be one, and then 3, 1, 1 would be another direction, and then 3, 2, 1 is another direction. There may be applications where those are way, way, way more handy. So the way to change this coordinates into those coordinates is by multiplying with this matrix. So this is the solution. And now I fixed it with a -5. But now we have the reverse problem. Okay. So example 5. Reverse, whoops. Reverse problem. Okay, so what is the matrix that takes coordinates from 1, 2, 3, 3, 1, 1, 3, 2, 1, which is W into 1, 0, 0, comma 0, 1, 0, comma 0, 0, 1, which uses the identity matrix columns. This is a little bit of abuse of notation because we usually call this the identity matrix. I'm using, again, I, not for the identity matrix, but for the columns of the identity matrix. So this is not very good notation. Please forgive me for that. But I didn't want to make the notation too complicated either. Yeah, so what is the matrix that takes us back? You know, what we did in example 4, we took A, B, C, all right, and then we multiplied with a matrix. I'm going to call it C for now because that is a change of, so this is in coordinates in the standard basis. And we went into, so we multiply with A, B, C to obtain a new vector X, Y, Z, which are the coordinates on the weird basis. All right, so the C we found in example 4 is 1/8 of -1, 0, 3, 4, -8, 4, -1, 8, -5. Okay, so we went from standard using this matrix to get to the weird. Okay, so that is from example 4. But now we have the reverse question. Let's say you are given X, Y, Z, and we want to come back to A, B, C. Think about that. So again, we have A, B, C multiplied on the left by C. So that is C. And we want to end up with X, Y, Z. So what if we start with X, Y, Z and we want to end up with A, B, C? Well, what we have to do, literally, is multiply on both sides by the inverse matrix. So once you have one direction, the other direction is fairly straightforward. We have to find the inverse matrix. And that will do. So let's find the inverse of C. At this point, I suggest you pause the video for a moment so that you can find the inverse on your own, perhaps using the Gauss-Jordan elimination method, or if you want to use cofactors. So take the time to find the inverse. Pause for a moment. I'm going to just tell you what the inverse is, but I don't want to use video time to go over the Gauss-Jordan elimination method, even though it does have value to do that. I'm not going to do it. I just want you to please find the inverse. So take a moment to find the inverse. Pause for a moment. And if you're back, if you haven't figured out the inverse on your own, try to find it. Second chance to pause and find the inverse of this matrix. Okay, I know you want to. So the inverse is, let me double check with my notes. It is 1, 2, 3, 3, 1, 1, 3, 2, 1, which is made up after we compute this exactly by the coordinates of by the column vectors of the weird matrix. So this is the weird matrix. So isn't that very, very interesting? So in order to figure out example 4, so after the fact, okay, to do example 4, we could have the matrix above made up by the weird vectors and find the inverse. As simple as that. That's why oftentimes we do it this way, because this is way faster. Yeah, so this is the matrix that goes from the weird. Let me double check. This is example 5. There it is. Example 5 is about going from the weird to the standard basis. So for instance, now let's make sure we understand this. So what is 1, 0, 0 in weird coordinates? It is a 1, 2, 3 vector in regular coordinates. If I want to transfer that to regular coordinates, all we have to do is multiply by C inverse. So 1, 2, 3, 3, 1, 1, 3, 2, 1. So again, this is, remember what 1, 0, 0 in weird coordinates means. It means one of those. So if we want to transfer that into regular coordinates, all we have to do is say, just multiply. So that is 1, 2, 3. And now we are in regular coordinates. So this is the answer, by the way, of example 5. We're finished with that. And it turns out that it works. So to go from weird coordinates to standard coordinates, use this matrix. If we want to go from what is it called? From identity, from regular coordinates into weird coordinates, then multiply by the inverse of this, the one that has the 1/8. Okay, let's look at a new example. 6. All right. Find the matrices to go from and to basis. So now we have a new weird basis. I'm going to go back to our example. I think it was example 3. Yeah, example 3 is where we started the complication. Yeah, I'm kind of getting excited because we're going somewhere. So now instead of the weird basis being 1, 2, 3, 3, 1, 1, 3, 2, 1, I want to use 5, 6, 7, 0, 1, 2, -2, 0, 1. So we want to use the basis 5, 6, 7, 0, 1, 2, and -2, 0, 2. And we have to come up with a name for this weird basis. What is a good name? So W for weird, R for rare. I'm just coming up with some kind of letter. Okay, so now we are asking for 2 matrices. The one that goes from the regular to this rare, I'm just going to call it rare, weird, rare basis and back. Now, let's not work as hard as we did in the previous problem. Let's see. Because there's one that is super easy. We know there is a matrix. If we just do 5, 6, 7, 0, 1, 2, -2, 0, 2. This is one of the 2 matrices. This should be, let's call it D inverse. And what does D inverse do? Let's see, 1, 0, 0. It takes us from our coordinates, to I coordinates. Yeah, example 5 was that, reverse problem. What is a matrix that takes coordinates that are weird into normal, weird into normal? Yeah, so that's the matrix, and that's the one we found. And we label it as C inverse because it was the inverse of the example 4. So we got 1/2 half of the problem done very, very quickly. Okay, so that takes us from r coordinates to regular coordinates. And now we want to find d, which is the one that takes us from regular coordinates to these weird coordinates. Yep. So let's find the inverse of this matrix, which is the inverse of the inverse of d, which is going to give us d. All right. We have a problem when we try to find the inverse of this. There is no inverse. Yeah. So there is no inverse for the inverse. Yeah, I'm labeling this as the inverse, but assuming that there was going to be an inverse of the inverse, but there isn't one. And the reason is because, after all, because I came up with these vectors at random, I didn't realize that those are not linearly independent, and consequently, they cannot form a basis for R3. That's a bummer. So 5, 6, 7, 0, 1, 2, and -2, 0, 2 is not a basis for R cubed, because the vectors are not linearly independent. That's a bummer that they're not. Let's pretend they were. So if I was asking for that, the question would be wrong. Why would it be wrong? Because in order to go from one basis to another basis, we have to have a basis. This is not a basis. There's a linear combination of two of them that gives us the third one. And so we cannot really produce all of R cubed. We cannot generate all of R cubed. In other words, there's going to be vectors that are going to be outside of the span of those, and so we cannot do that. But let's move on to the general idea. Yeah. So the general idea. General idea of what's going on right now. Okay, so we have a linear transformation. So you got R cubed going into R cubed with a linear transformation T. Okay, and there's a matrix corresponding to that. So A will do that if you multiply with nice a coordinate, a vector, which is written in standard basis, and the answer will be given with a standard basis. Okay, so that does work, and that's one of the first couple examples were about finding this A, and that has complications. Example 3 had complications, but we were able to find the matrix A. Okay, so that is the idea right now. Now, what if instead of giving you the coordinates in standard basis, we give you coordinates in weird basis? So weird basis coordinates, and we want to find the same answer. Now, those two are not going to be the same because, yeah, those two are not going to be the same because the problem is going to be given in weird coordinates. And then we want to find the answer in regular coordinates. So that is the question. What matrix should we multiply? If we already know A, mind, if we already know A, what matrix should we multiply those coordinates in W to get the same answer? And those two are not going to be the same. Well, we can piggyback on the answer from above. We can change W coordinates into I coordinates. And if we look back into example 5, okay, we want to, what is the matrix that takes weird coordinates into regular coordinates? And it would be this guy. Weird coordinates into regular coordinates is what we call the inverse of a matrix. It would be C inverse. So we can multiply by C inverse. That will give us the coordinates into regular coordinates. And then we can multiply by A. And that does the job. Isn't that cool? That's the cool part about it. In fact, we can do that now. So yeah, we can probably make an example out of that. So we can take this matrix multiplied with A, and that gives us a new matrix that takes weird coordinates, vectors in weird coordinates, applies the transformation. So we multiply those two to get a new matrix. Let's call it S for now. Okay, a new matrix. And this matrix takes vectors in weird coordinates, applies the transformation, and puts it into regular coordinates. Now, what if we see, it's a bummer that example 6 failed because this is not a basis. Let's pretend for a moment that that was a basis. And so, and let's pretend for a moment we wanted to change the answer into these weird coordinates. Yeah, from our coordinates to, so had there been a D that would have worked, then this is the matrix. There isn't, but had there been one, this is the matrix we would be using, which is the inverse of that, to go from I coordinates to R coordinates. So we can apply D A C inverse to weird coordinates to get the answer into R coordinates. So in a nutshell, we're using those matrices as interpreters from one language to another. This matrix takes W language into standard language, I language. A transforms, and then D puts it back into this other language. Now, so this is the third bullet. Remember at the beginning of the video, there were 3 bullets, rather 4 bullets. This is the third bullet we want to arrive to. Yeah. So this is the third bullet. Now, if the weird basis, if we want to transform a vector given in weird coordinates so that the answer is in weird coordinates, then, so we have a vector in weird coordinates, put it in, C inverse puts it in standard coordinates, A transforms the vector, and then C puts the answer back into weird coordinates. So this is the input, and this would be the output of the transformation T going from starting with weird coordinates and ending with weird coordinates. And actually, we couldn't do that. We could do this. So this is, before I continue, this is the fourth bullet, which is this uh, a narrowing of the third bullet, because here we could have three total identity coordinates, which are just the normal coordinates, weird coordinates, and rare coordinates. And these are going to be weird and weird coordinates. Um, yes, yes. So we could do that now. We could find the matrix, which is found by multiplying those three. And by the way, um, matrices are not commutative. So it is not the case in general, not the case that somebody could say, well, if I'm doing CAC inverse, why don't I just do, commute those two? So ACC inverse, and that is equal to A times, well, C times C inverse is the identity, which is true, and that is just A. Of course, that's false. And the reason why is because this step is incorrect. Yeah. Matrices are not commutative. In some rare cases they are, but in general they're not. They're not. So we cannot just switch those two around. So the matrix CAC inverse is the one that will take us from one. So what does that do? A is T going just using regular coordinates. It's a matrix using regular coordinates. C inverse takes weird coordinates into regular coordinates. Then apply this, and then what we obtain is a regular coordinate. So if we wanted to go back to weird coordinates, we have to apply C. So we go from regular coordinates back to weird coordinates. We start with weird coordinates, and we end up with weird coordinates if you wanted to. And that would be the matrix that will do that. All right, we're gonna stop the video here.